Yeah, hi everyone. I'm GreklekMcKeon. I'm a final year grad student here at Caltech, and I've been working on characterizing small planet compositions. And when I say small planets, I mean everything below pretty much 3-ish Earth radii, including the rocky super-Earths and the rock plus gas sub-Neptunes, and the in-between planets that may or may not be water-rich, depending on who you ask. And when we measure the masses and radii of these planets, we can think about their bulk density and how that maps to possible compositions. And there's a lot of interest in these small planets orbiting M-dwarfs because despite all the challenges that M-dwarfs pose with their activity for planet characterization, as we've heard about this week, thanks to the relatively large planet-to-star radius and mass ratios, small planets around M-dwarfs represent our best opportunity to measure the atmospheres of rocky planets with current instruments. And so there's a lot of interest in this population, but also a lot of debate that continues to rage on with many open questions, including how common are the water worlds and which planets get to keep versus lose their atmospheres, and what governs the transition from sub-Neptunes to super-Earths, and what processes carve the radius valley, and many more, and I will answer none of those questions in this talk today. I'm just going to talk about some efforts that I've been working on to do what everyone does when they don't have clear answers on this population, and that's get more data. So by adding a lot of planets to this mass radius diagram and precisely measuring their masses and radii, we can start to think about trends in bulk density and composition. And I've been working on this with observations mostly from the 5-meter telescope at Palomar Observatory. And we're looking at 8 multi-planet systems containing 19 planets with their radii marked with the pink lines there. And these are all systems originally discovered by TESS that have planets near a mean motion resonance, and they have TTVs due to dynamical interactions between the planets, and we can use those to precisely measure the masses and radii. And 2 of the systems from this survey I've already submitted papers on, and they're out on arXiv, and you can check those out if you're interested, but people come to conferences for the new exciting stuff. So I'm going to talk about preliminary results from 2 systems that have planets that are in this ambiguous region where their bulk density is consistent with either a rock plus hydrogen composition or a rock plus water composition, and they also contain another planet of a different bulk density. And the way to differentiate between those degenerate compositions when all we have is planet mass and radius, well, one way is to just observe it with JWST and quickly determine whether the planet has a hydrogen-rich envelope. And as much as I would love to just observe every planet with JWST, the TAC keeps telling me I can't do that. So we need another way to try to break degeneracies in planet composition with just mass and radius. And one way to do that is to characterize the stellar XUV irradiation. And one way to do that is with the XMM Newton Space Telescope that can measure X-ray and UV photons for the host star. And then we can think about the atmospheric mass loss rate and the atmospheric mass loss timescale for these planets and use that to rule out a rock plus primordial low metallicity hydrogen-helium envelope and argue in favor of a higher or a more volatile-rich or water-rich composition for these kind of ambiguous planets. And this is not a technique that I invented. It's been applied to many other systems before, but the more planets that we add to this mass radius stellar XUV parameter space, the more carefully we can think about potential trends in composition for small planets. So the first system that we've applied this to that I want to talk about is TOI 2096. Which is a cool 3300 Kelvin M-dwarf that has pretty quick 4.4-day rotation that was detected in the TESS photometry, and large flares exhibited in most of the TESS sectors, 10 to 20% relative flux increases in the TESS bandpass. And we measured the masses and radii of the planets with TTVs and found that the inner super-Earth planet has a bulk density consistent with an Earth-like composition, while the outer sub-Neptune planet could either have Earth-like rock plus about 30% water by mass, or it could have less than about a percent hydrogen envelope and be consistent with the bulk density. So we submitted a proposal for XMM Newton and stared at it to try to determine between those 2 scenarios. And when we think about TOI 2096 the rotation period of this star relative to the population of all M dwarfs that have measured X-ray luminosities and measured rotation periods. We can see it's in this saturated regime of the fast rotators where the X-ray luminosity is higher. And based on the distribution of the population, we expected the X-ray flux to be somewhere in this range. And we stared at it for a while and got very few photons. The actual flux of TOI 2096 that we measured was way down here. So at least at the time that we measured this star, TOI 2096 was one of the most XUV quiet planet hosting M dwarfs with a rotation period faster than 10 days. So unfortunately, for this system, we weren't able to rule out the hydrogen-rich envelope scenario, and the composition remains degenerate. So let's try a different system. Here's the TOI 406 system, which is very similar in that it hosts an inner super-Earth planet consistent with an Earth-like composition and an outer sub-Neptune-sized planet with ambiguous composition based only on its bulk density. But this star is much more quiet. It doesn't have visible flares in the available ground-based photometry, and it has a longer 30-day rotation period. So we stared at this star with XMM Newton for a lot longer, for 3 times longer, to ensure that even if the X-ray luminosity is a lot lower than the population distribution near this transition from the saturated to unsaturated regime, we would still be able to detect it. And the result was we were wrong. We couldn't detect it. We didn't get any photons from TOI 4. Well, we did. We got background photons for TOI 406. And so what we were able to do was place a 95% upper limit on the X-ray luminosity of this host star, and again, couldn't break the degeneracy in planet composition for this system. But what we can do is start to think about, for these systems where we add this X-ray luminosity or X-ray irradiation characterization, we can say, are these systems with planets of different compositions consistent with a primordial difference in composition? In this case, we can't answer the question for these systems. Or are they consistent with evolution pathways that lead to different planet compositions, like photoevaporation or core-powered mass loss? And in this case, for both systems, the answer is yes, they are potentially consistent with that. And as we add many more systems to this parameter space, hopefully we can begin to identify trends in planet composition that are related to stellar XUV flux. And there are many accepted XMM Newton and Chandra and HST proposals that will do a similar analysis, and I'm looking forward to the results of those. OK, now time for a caveat about the TOI 406 system, where the masses were originally measured with RVs, and then we followed it up with transit timing variations in an attempt to improve the mass and radius constraints. We expected relatively weak TTVs, around a minute or two, but what we ended up finding in some work being led by Yale PhD student Kendra Wen was that the TTVs are a lot larger than expected, about 10 minutes peak to peak for the outer planet. And there are 2 possible explanations for this. One is that the planets have eccentric orbits on the level of 0.1 or 0.2, which is unlikely given tidal circularization timescale arguments, or that there's an undetected third planet in the system that's near an orbital resonance with the outer planet and is dynamically exciting its eccentricity, creating a forced eccentricity at a low level. And in either scenario, that either dynamically forced eccentricity or larger eccentricity that's producing the TTVs purely can produce tidal heating in this planet, which may be important for its interior and atmospheric composition. And that's not just true for TOI 406. There are a lot of systems that this may be important for. So here I'm showing the JWST Rocky Worlds Director's Discretionary Time Targets Under Consideration list. These are all the rocky planets that the community has decided are our best opportunity to search for atmospheres. And now I'm going to put a red star over all of the planets in this sample that are near a first or second order mean motion resonance. It's a lot. And when we look at this subset of planets that are near mean motion resonances and therefore might have dynamically excited forced eccentricities, these are all the systems that are already scheduled for JWST observation minus TRAPPIST-1. So there are potentially a great many number of systems that have this eccentricity-driven tidal heating effects, which we're starting to see some of the results of now. For example, there was a recent result this week about the super-Earth L9859b, which may have an outgassed sulfur-rich atmosphere, and tidal heating in super-Earth planets can affect the mantle melt fraction and outgassing rates. And in sub-Neptunes, it's also important to think not just about the radiation coming down on the planet from above, but the tidal heat flux coming up from below. And for planets like the 1266 system, which I have a paper on arXiv about, we believe that its sub-Neptune hydrogen-rich envelope may be inflated by tidal heating. And we were able to use really precise M-dwarf refractory abundances from the Canon, which Ida Bamar gave a great talk about on Monday, to measure the iron, nickel, silicon, oxygen, and magnesium abundances in the planet, which are all overlapping with Earth-like composition to say this planet likely has an Earth-like core mantle composition, and therefore the outgassing rates may be similar to in our own solar system. And yeah, so I'll just conclude now by saying that we can use TTVs to precisely measure planet densities, and in some cases, the stellar XUV fluxes can break degeneracy and composition. And for the subset of those planets that may have tidal heating as an important property, we can use stellar refractory abundances to think about how that tidal heating may impact a given planet's internal composition. Thank you. I'll take questions now.
Hey, pencil question, grad student. Yeah. Well, the only person with a hand up.
Hi, Anish Babra, UC San Diego. This might be a naive question, but is it possible that the TTV that you saw, discrepancy that you saw, could be due to stellar activity or?
For the TOI 406 system?
Yeah.
Not at the 10-minute level. Changes in the stellar photosphere and spots and stuff like that could shift the transit time slightly, but that's like a minute level effect. Yeah.
Okay.
Free for all so far.
Hey, great talk. So a lot of people really want to find atmospheres on some of these rocks, and if they're near mean motion resonances, then that will excite their eccentricities, and that will make scheduling eclipse observations challenging. Do you have insight on how well constrained eccentricity is from this kind of TTV analysis? And a separate question, what's your theory on why these stars are so X-ray faint, and what are the challenges of using that telescope?
Yeah, so for the first one, the TTVs are observationally sensitive to eccentricities on the 0.01 level. So the eclipse timing offsets, they can be significant if you have a short window, but sometimes it's okay. And the dynamically forced eccentricities are usually at the 0.001 to sometimes 0.01 level. So they sound very low, but they're super important for close-in systems. It can still have a big tidal heating impact. But in terms of the eclipse timing offsets, it's probably not an issue. And then for the reason why these stars are so XUV quiet, I have absolutely no idea. And if anyone has ideas, please let me know. Yeah.
One last quick question. Yeah, over there. Please.
So we saw in another talk that the argument that when you get towards mean motion resonance, it seemed to be water-rich worlds, but now you're suggesting with planets that are in mean motion resonance where they have TTVs, maybe they're actually being tidally inflated. So does that mean do you see on a population level occurrence that planets that have TTVs are low density?
Yeah, there definitely has been population level analysis of the TTV versus RV population in the past to argue that the TTV planets are low density. We don't have enough from our survey yet to comment on that. And for the TOI 1266 system that has a potentially inflated radius, the only reason we could make that argument for that system is it has an inner sub-Neptune and an outer super-Earth that's inconsistent with photoevaporation. So we needed another way to explain the larger radius for the inner planet, and that was the only one that was tidally heated. So that was the argument there.